Imagine for a moment, really picture it, not just, visiting the moon, but actually building a home there, a permanent one.
Hmm.
What would that really take? I mean, to live there, properly live there long term, it's not just the trip, right?
Oh, absolutely not. It's the day-to-day survival once you arrive, the
Yeah.
basics.
Exact.
And that's where you hit this enormous wall. Just think about the cost, the sheer logistics of hauling essentials like water or even oxygen all the way from Earth.
It's mind-boggling.
Yeah, it really is. Some studies, they put a number on it, something like $83,000 just to ship 1 gallon of water.
$83,000 for a gallon.
Yep. And think about this. Each astronaut, they need about 4 gallons a day just to drink.
4 gallons. Wow. Okay, so that cost alone, I mean, it makes any kind of long-term stay seem, well, basically impossible.
Yep.
Unsustainable.
Completely. It really gets to the heart of the problem.
So it forces the big question, doesn't it? What if you didn't have to ship everything? What if somehow you could make those vital things, water, air, maybe even, I don't know, rocket fuel right there on the moon using what's already lying around?
Precisely. And that's the vision. That's what's pushing some really fascinating research forward.
Okay.
Which brings us neatly to what we're diving into today. There's this recent breakthrough from a team of scientists in China. They published it in the journal Joule just this July 16th. And they're claiming essentially a one-step method.
One step? For what?
To get water and produce oxygen and methane straight from moon dust, regolith, and the power source. Just focused sunlight.
Wow. Okay. Focused sunlight. All right. So that's our mission for this deep dive then. Let's unpack this. This potentially, game-changing tech. Explore what the scientists are calling the magic of this moon dust. Understand what it could mean for actually living on the moon.
But also critically, right,
Yeah.
we need to look at the hurdles.
Absolutely. The big challenges, the skepticism from other experts, because let's be real, turning this into something that actually works up there, that's a whole other story.
It certainly is. So the core idea, it hinges on using the lunar soil itself. You see, the moon actually has quite a bit of water. It's just not, flowing in rivers.
Right, it's trapped.
Exactly. Delivered over eons by comets, asteroids, the solar wind, and it gets locked into minerals, things like ilmenite, especially, we think, in those super cold, permanently shadowed craters near the poles.
Okay, and usually the idea was just to heat the regolith up, right? Cook the water out.
That's been the main approach, yeah, just heat it and capture the water vapor. But this new Chinese research, it adds a really interesting twist. They've taken it a significant step further.
How so?
Their method, it involves heating the regolith, yes, to about 392 Fahrenheit, 200 Celsius, using focused sunlight. And that releases the water, the H2O, trapped inside.
Okay, standard enough so far.
But then, here's the clever bit. They add carbon dioxide, CO2, which could even potentially be the CO2 exhaled by astronauts living there.
Recycling breath. Okay.
And the key ingredient here is that ilmenite mineral we mentioned, which is pretty abundant in lunar soil.
Yeah.
It turns out its composition, the iron titanium oxides in it, lets it act as a catalyst.
A catalyst, meaning it helps the reaction happen.
Precisely. It speeds up the chemical reactions between the water they just extracted and the CO2 they added. But crucially, the ilmenite itself isn't used up in the process.
Okay.
And this whole thing, they call it photothermal catalysis. It's pretty neat because it uses that focused sunlight not just for heat, but also to directly energize and drive these chemical reactions in the soil. Light becomes part of the engine, so to speak. That's why they can call it a single-step method.
Right, so it's not just heating, it's heating and using the light to drive the chemistry in one go. So the big breakthrough, the really revolutionary part, is this single integrated process, taking moon dirt, basically, and turning it into water, oxygen, and rocket fuel. All three critical things.
That's the claim. And a huge advantage they're highlighting is that unlike maybe other ideas, their process doesn't need, complicated multi-stage machines or some special catalyst you'd have to lug all the way from Earth.
Which means potentially using energy better, less complex gear, lower costs.
That's the hope. And what's really novel is using the soil itself as the catalyst to essentially crack CO2 molecules and mash them together with the water to make methane, CH4.
Methane. Why methane specifically?
Well, that choice is actually quite insightful. Think about storing fuel. Liquid hydrogen, the classic rocket fuel, needs incredibly low temperatures, complex cryogenic storage.
Yep.
Methane, much more stable, easier to handle.
So it simplifies things.
Massively. It's not just a small technical detail. It could be a game changer for the whole lunar logistics setup. Makes the infrastructure simpler, cheaper, for the rockets linking Earth and the Moon. Lots of commercial space companies are already betting on methane rockets for exactly this reason.
Okay, this really does sound incredibly promising for, actually setting up shop on the moon, making it feasible. But what are the catches? What are the big challenges they still need to overcome? It can't be that straightforward, can it?
And that's where you get some really important reality checks. Folks like Philip Metzger, he's a planetary physicist at the University of Central Florida, wasn't involved in this study. He offers some critical perspective.
Okay, what does he say?
He acknowledges it's novel, definitely interesting science, but he's skeptical about how viable it is right now for practical use. For instance, think about heating that regolith. Lunar soil is actually an amazing thermal insulator.
An insulator, so it doesn't conduct heat well?
Terribly well, which means getting heat to penetrate deep down efficiently through a whole batch of soil. That's really tricky. The heat just doesn't spread easily.
So you might only cook the surface layer effectively.
Potentially, yeah. Or it takes a very long time, which could seriously limit how much water you can actually produce in a reasonable time frame.
Right. I can see how that throws a wrench in the works. You need volume, you need speed if you're supporting a base. So how does that thermal problem affect the whole one-step idea?
Well, it means that while the chemistry might work beautifully in a controlled lab setup, probably with a simulated soil that behaves nicely, scaling it up on the moon is another beast entirely.
Okay.
One idea to get around the heating problem might be to, say, tumble the regolith. Keep mixing it, turning it over so it heats more evenly.
Makes sense.
But now you're introducing moving parts.
Yeah.
And on the moon, with that super fine abrasive dust that gets into everything and those wild temperature swings, we're talking differences of up to, 482 degrees Fahrenheit between lunar day and night?
Yeah, that sounds like a recipe for mechanical failure.
Exactly. Metzger's point isn't that it's impossible, but that the technology needs a lot more development, more maturation, to prove it can actually compete with other methods and survive up there.
Okay, so heating efficiency is one major hurdle. What about the ingredients for the process? Any issues there? You mentioned the carbon dioxide.
Yes, that's another big one. Both the research team and Metzger flagged this as a potential bottleneck. The question is, can astronauts realistically produce enough CO2 just by, breathing?
Can they?
Metzger did some back-of-the-envelope calculations. He reckons astronauts might only supply about a tenth of the CO2 needed for this process to work at scale.
Only a tenth. Oh. So where does the rest come from?
Well, the only other option is you ship it from Earth.
Right back to square one.
Pretty much.
Right.
Which, as you can imagine, kind of defeats the whole purpose of developing a cheap, self-sufficient way to make resources on the moon. It's like building a factory that runs on worker size.
Yeah.
Just not enough input.
So if you're still shipping a key ingredient like CO2 from Earth, the whole value proposition, the cost saving, it just evaporates, doesn't it?
It diminishes significantly, yeah.
Which then raises the question, are there other ways to do this? Maybe more efficient ways, even if they seem more complex initially.
Metzger brings that up too. He mentions a similar experiment that used a different kind of catalyst, something called nickel-on-kieselguhr. Sounds exotic, right?
Definitely sounds like something you'd have to ship from Earth.
Exactly. It's a material specifically designed to be a catalyst. And his suspicion is that something like that, engineered for the job, would likely be much more efficient than just using plain old lunar regolith.
Okay, but then you're back to shipping costs again, at least initially.
True, shipping that catalyst would be expensive up front. But here's the thing. Catalysts aren't consumed in the reaction. They're reusable. So, over the long term, if you run a cost-benefit analysis, it might actually turn out to be more efficient, more productive, than relying solely on the less efficient, though free, lunar soil.
That's a really interesting trade-off. Initial cost versus long-term efficiency. Okay, so putting this all together, what's the final verdict on this Chinese research? Is it a genuine game changer for lunar settlements, or is it more like an interesting lab curiosity for now?
I think the fair assessment is that the research team has definitely shown something important. They've proved, scientifically, that yes, you can use lunar regolith itself as a catalyst to make fuel and water this way. That's a real step forward in understanding the potential of lunar resources.
Okay, a proof of concept.
Exactly. The next crucial step, though, is the engineering one. Can they demonstrate that this specific technology can be scaled up effectively? Can it produce enough resources to actually sustain a lunar base more efficiently than other techniques we might develop? And critically, can it operate reliably, day in, day out, in that incredibly harsh lunar environment?
Right. The weak gravity, the temperature chaos, the radiation. It's not exactly a friendly place for sensitive equipment.
Not at all.
Okay, this has been really fascinating. We've looked at this incredible idea using moon dust, regolith, as a catalyst to make water, oxygen, fuel right there on the moon. It's such an elegant, ingenious
It
vision.
really is appealing, conceptually.
But then we've also hit these very real, very practical roadblocks, the engineering challenges, like how tricky it is to heat that insulating regolith, the whole CO2 supply problem, the points raised by experts like Philip Metzger.
It's that classic tension, isn't it? Scientific possibility versus engineering practicality.
Yeah.
What seems clear is, look, a permanent moon base isn't suddenly going to pop up next year. NASA's Artemis III mission, the next planned landing, they're aiming for 2027, and that's probably optimistic.
Still feels a long way off.
It is, but these kinds of experiments, the ones that will get tested during missions like Artemis, they are absolutely vital. They're the proving ground. They'll tell us whether humanity can really figure out how to live on the moon sustainably, beyond just planting a flag and coming home.
That really is the ultimate question, isn't it? So, thinking about everything we've discussed, making water oxygen fuel, dealing with the regolith insulation, the dust, those crazy temperature swings, what specific area, what piece of science or technology do you listening think is the absolute most critical next step? What's the key thing we need to unlock to truly establish a self-sustaining human presence on the moon? What puzzle piece, in your mind, will finally let humanity live and thrive off-world?